Hi, this is Mrs. Kidman, and in this video, we are going to be discussing proportionality theorems of triangles. So what does that mean? Well, basically, it's a relationship that exists in a triangle when when we either have an angle bisector or a line that's parallel to one of the sides. Let's take a look at a couple different theorems here. The first one that we're going to look at is the triangle proportionality theorem, which says if a line is parallel to one side of a triangle and it intersects the other two sides, then it divides the two sides proportionally. So what that means is this line here, as it acts as being parallel to this line here, that this RT over TQ is going to be the same proportion as this RU over US. They're equal in proportion. Now, that doesn't mean that RT is equal to RU or anything like that, or even that TQ is equal to RT. What it means is that if I divide RT by TQ and RU by US, that they will be equal in those proportions. So let's take a look at a couple of examples like that. Now, in the converse, what we also know is that if those sides are proportional when they're cut by a line segment, what that means is that line segment and that other side of our triangle that is not cut by that line or not intersected by that line are also going to be parallel. So it works in that converse, that if the lines are parallel, then the sides are proportional. If the sides are proportional, then the lines are parallel. So let's take a look at a couple of examples here. This first one says in the diagram, segment QS is parallel to segment UT. And so what that means here is we know that RS is 4, ST is 6, and QU is 9. How can we figure out what the length of RQ is? Well, we just said that they're proportional. So we can look at that proportion of RS divided by ST, and it should be equal to RQ divided by QU. So let's take a look at, after we substitute these in, what that would look like. So RS is 4, ST is 6, RQ is, we don't know yet, so we've got RQ divided by QU, which is 9. So those are all of our different sides there. So now based on that idea, what we can do is figure out what that proportion is. So 4 over 6 actually simplifies into 2/3. And so that means they have a 2/3 relationship. So if RQ over 9 is equal to 2/3, well, 3 times 9 equals 3 times 9. Oh, 3 times 3 equals 9, which means that that means that we have to multiply 2 times 3 to get RQ, and 2 times 3, as we know, is 6. So this side is actually 6 because we know that 6 over 9 is also going to be 2/3. Okay, let's take a look at one more example here related to these two theorems. Now, this one is a word problem. It says on the shoe rack shown, BA, or this distance here, is 33. So let's add that in here. This length is 33. Perfect. And then CB up here is 27 centimeters. And then we also know that CD is 44 and DE is 25. And what we want to figure out is, why is it not parallel to the floor? Well, we know by that converse to the proportionality theorem that in order for these two lines to be parallel, they have to have the same proportions. But we're looking at the proportion of 27 over 33. And we're asking ourselves, is that equal to 44 over 25? Well, we can easily say no, because in this case, we know that this is going to be less than 1. But this one's going to be greater than 1. Now, because one's less than 1 and one's greater than 1, there is no way that they can be equal to one another. Therefore, that line BD is not parallel to AE. And because AE is the same as the floor, that shelf is not parallel to the floor. In order for it to be, we need these two proportions to be equal to one another. So that's kind of how those theorems apply. Now let's take a look at this next one. This says 3 parallel lines theorem. If 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. So these, again, are proportionality theorems. Some are related to triangles, some aren't. Now in this case, it's just saying if I have 3 parallel lines and they intersect 2 transversals, those transversals will be divided proportionally. And it makes sense because those parallel lines will never intersect, so the distance between them stays the exact same. Therefore, even though the transversals might intersect, the distance that they're being cut is all proportional. So let's take a look at how we can apply this one. So in the diagram over here, 1, 2, and 3 are all congruent. Angles 1, 2, and 3 are all congruent, labeled in red. GF here is 120 yards, DE is 150, CD is 300, and we want to figure out what HF is. So what this whole long distance is. So how can we do that? Well, what we know is this line, and this line are all parallel. These streets are. So if they're all parallel, that means that this line FH right here, the line FH and the line CE are both transversals cut by that, meaning that their proportions are the same. So as we refer back to this theorem here, it says that UW, or this piece over this piece, should be the same as this one over this one. So we can use that same idea here, that this piece over this piece should be the same as this piece over this piece. And then once we have that, we can add those two sides together to figure out what that is. So we know that 120 over GH is going to be equal to 150 over 300. Well, 150 over 300 actually simplifies into 1/2. So we know that this one also needs to simplify into 1/2. So what number does GH need to be to make it 1/2? Well, that means that this is going to be 240 yards. And so because that's what 240 is, we know that FH, or that long piece, is going to be 120 plus 240, or it's going to be 360 yards long. And we can use that. Similarly, we could have also done that proportion of FH over 120 by looking at the relationship between ED over EC. There's a lot of different ways that we can solve this, which is the really cool thing. Now, we've got two more examples here. This next theorem is called the triangle angle bisector theorem, which basically says that if a ray bisects an angle of a triangle and it divides the opposite side into segments whose lengths are proportional to the lengths of the other two. So what that means, you can kind of see this here, that as we get this angle bisector, meaning these two angles inside are the same, that this distance AD over DB, so this side over this side, is equal to this side over that side. Isn't that crazy? I think that's so cool. So let's apply this one time. So in the diagram, angle QPR is congruent to angle RPS, meaning that PR is our angle bisector here. So using the given side lengths, we want to figure out what RS is. Well, we know, as we've learned before, that QR over RS is equal to QP over PS, right? That this side over this side is equal to this side over this side. And we want to make sure that we have those matching sides. So notice how it's this point on top and the B's on the bottom. We want to make sure that we're consistent here. So in this case, we've got our Q's on top and our S's on bottom. Perfect. So then let's write those proportionality statements. Well, we know that QP is 7 and SP or PS is 13. But then this other one, we only know what QS is. And so that means that if this whole thing is 15 and this piece is X, this piece needs to be 15 minus X. So 7 over 13 is equal to 15 minus X over X. Now, how can we solve this? Well, a really easy way is we can do that cross-multiplying method where we multiply these two and multiply these two and set them equal to each other. And really what that's doing is we're multiplying both sides by 13 and then multiplying both sides by X to get rid of those denominators. But by cross-multiplying, we do it in one simple step. So let's take a look at what that ends up being. We get 7X on this side and 13 times 15 minus X on this side. So as we multiply that out, we can see that 13 times 15, we're going to use that distributive property, gives us 195. So we get 7X equals 195 minus 13X. Well, we can add that 13X to the other side and get that 20X equals 195 and divide both sides by 20. And we end up getting that X equals 195 divided by 20, or 9.75. Fantastic. So we can use this idea and kind of apply all those different things. Now, the last type of question that I want to look at is one where it says find the coordinates of point P along the directed line segment AB. So the ratio from AP to PB is 3:2. So what this means is overall, we want something that's a length of 5. So we've got a length of 5 here, or a distance of 5, and we want AP over AB to be equal to 3/5, and we want PB over AB to be equal to 2/5. So then we need to figure out where does that need to go. Well, what we can do is we can actually multiply one of these ratios, it doesn't matter which, by our slope to figure out how far we need to get. Now, if we're doing times 2/5, we need to start at B and go back because it's related to point B. If we're multiplying times 3/5, we want to use point A. So what we want to do is figure out what is that slope or that rise over run from this distance here, or how far are we actually going? So right here, we're going up 6 and we're going over 3. And so because we're going up 6 and over 3, what that means is I want to go up 3/5 of 6 and over 3/5 of 3 from point A. So let's figure that out. What is 3/5 times 6? Well, that's going to be 3.6. So really, I want to go up 3.6. 1, 2, 3.6, which is like right here. And then we need to go over 3/5 of 3, which is 1.8. So then we'll go over 1.8. And we end up right here. So this point right here is point P. Now again, notice what we did here is we took our slope and we did our rise over our run, and we just multiplied our rise times 3/5 and our run times 3/5 to figure out where that point would be for point P. So in the end, if we wanted to figure out what those coordinates of point P are, what we have to do is take our A value, which was 3, and add 3.6, just like we did, and take our Y value, which was 2, and add that 1.8, which was 3/5 of 3. And that will end up getting us that point P is 6.6 and 3.8. And we can see that that's where this is, right? That this went up to 6.6 and over to, oh, wait. Up 3, 6 point. Oh my goodness. Yes, I have that labeled wrong. We want to switch those. We went, our Y added 3.6 and our X added 1.8. I apologize for that mistake there. So it is 4.8 and 5.6, which is how we ended up getting that point there. Fantastic. So do we see how we got that? Awesome. So if you have any questions, those are different ways that we can use those proportionality theorems, whether it's on triangles, whether it's on lines, things like, or anything like that, to determine what some of those ratios are. If you have any questions, feel free to reach out, but that is proportionality theorems.